Hello, and welcome to our program, Astronomy for Everyone. The topic for this month's show is a poor man's measurement of longitude and latitude. And here to talk to us all about it is Dr. Dale Partin. Dale, welcome to the program.
Well, thank you, Don. Good to be here. It's been a few years since the last time I was on.
Yes, it has been. Now, before we get into our topic, if you could take a minute or so to tell our viewers a little bit about yourself and your background.
Sure. I went to Carnegie Mellon University in Pittsburgh, studied physics and electrical engineering, got a doctorate back in 1978, worked in industry doing industrial research, had a great time doing that. Always was interested in astronomy. When I retired, I started teaching astronomy at Macomb Community College, which I really enjoy. And I'm the vice president of the Warren Astronomical Society. And I like to get out and use my telescope on the sky.
Well, there you go. Sounds like a good number of things to be active in. Now, why is longitude and latitude so important?
Well, you might as well ask, why is it important to have an address for my house?
Okay.
Your latitude and longitude is like your address on the Earth. It tells you the coordinates of where you are, how far above or below the equator you are, and where you are in an east-west sense. So from ancient times, people that sailed ships had to know where they were and where they were going by knowing their latitude and longitude. And many shipwrecks happened because they didn't measure that very well way back. And so there's a story there, but ultimately we wound up with today's system of latitude and longitude.
Okay.
And there are ways of very accurately measuring it. I'm doing a poor man's measurement of latitude and longitude for
Sort of the low-tech version?
yes, very low tech, as you will see.
So, the challenge of finding longitude at sea was kind of difficult until the invention of a reliable clock, right?
Yes, that's true. The clocks back then were not very accurate. And out in the ocean where the ship is bouncing all over the place, you couldn't use a pendulum clock because the ship kept tilting. So in Great Britain, a few hundred years ago, there was a prize given for somebody who could manufacture an accurate clock called a chronometer, or to keep time rather accurately.
Okay. With having that clock, it's my understanding that you would need to know what time it was, like let's say in London, Greenwich, and then set your clock accordingly, correct?
Yes. If you look at the slide I provided on this, I show the Earth in two views. On the left, it illustrates the system of latitude. On the right, longitude. If you look at the left, the Earth spins on an axis going through the South Pole to the North Pole. So the obvious place to put 0 degrees latitude is the equator. So latitude is measured as so many degrees north or south of the equator. As you go north from the equator up to the North Pole, that's at 90 degrees north latitude. The South Pole is 90 degrees south latitude. Here in Michigan, we're at something like 42 or so degrees north latitude. So that's the system for measuring angular position above and below the equator. If you go the other way, left to right, there's no obvious place like the equator to put 0 degrees. So people in Britain decided that an observatory in a place called Greenwich, England, was going to be 0 degrees longitude, and a line from the north to the South Pole that passes through Greenwich. It's called the prime meridian. And you can see other lines that go from the North Pole to the South Pole. Those are other meridian lines. So if the sun passes exactly over the prime meridian at exactly noon, then as the Earth rotates, other meridians have the sun passing over them. So it takes 24 hours, obviously, for the Earth to rotate once on its axis. And that's a 360-degree rotation in 24 hours. So that's 15 degrees per hour is the rotation rate. So if you measure the time the sun crosses your meridian, you can determine your longitude if you know the time. From knowing what time is where you are and how many hours away you are from Greenwich, England, when the sun crosses your meridian, you can figure out your longitude. And I'll show how I did that.
Okay, let's take a look.
So you next see a map of the United States or North America, South America. The green area is the Eastern time zone. Somewhere up the middle of that, it's exactly 5 hours after or away from Greenwich, England. Meaning if the sun passes above Greenwich, England at noon, 5 hours later, the Earth has rotated around where the Earth is passing right over the center of the Eastern time zone. So 5 hours, 15 degrees per hour, that would be 75 degrees west longitude. However, in the summer, because of daylight savings time, it's 4 hours difference in how we keep time. So I'd like to show you my very sophisticated experimental equipment in this picture.
All right, let's take a look at that, Dale.
It was sort of a low budget piece of equipment. I went to a hardware store and got a large piece of wood, and I have a bubble level laying there, and under each corner of that big piece of wood I have shims, and I adjust those shims until the bubble level shows me that the board is horizontal in both directions. I then have a weird looking metal piece supporting a metal rod that's coming up, casting a shadow. And I've put some shims under the near edge of that metal base to tilt it so that when I suspend a string from the tip of that metal rod down to the board, it hits the board, not the metal base. So I can put a little X right under the tip of that metal rod. Then I watch the shadow of the sun cross that board, and I have some computer paper taped onto the board. And every 5 minutes or so, I make a little X right at the tip of the shadow and write down the time next to it. So that's kind of crude, right?
Yes.
That's what I did. And so as hours pass by, the shadow of the sun moves from left to right. I have several little X's. When I'm done, I use this meter stick laying on the right side of that board to measure the height of the pole and the length of the distance from each little X on the paper to the point right at the bottom of that metal rod. And if I did this, for example, on June the 4th, 2005, where I live in Ray, Michigan. And if you look at the next slide, I show some data. On the horizontal axis of this graph, I plot the time in hours. So I'm using military time. So 13 means 1300 hours or 1 o'clock in the afternoon. 14 means 1400 hours or 2 p.m., so forth. And on the vertical axis, I plot the shadow length that I measured with my meter stick. You can see that at about roughly 1:30 in the afternoon, the shadow length got small and then started getting big again. So when that shadow was the shortest it was going to get, that's when the sun passed right over the meridian that went right over my head. That was true local noon. And knowing that time, I plotted the data and found a sine wave that fit the data pretty well. And right at that minimum, getting that time is 1:29 p.m. is all I need to get my longitude. But I got something else that you'll see the importance of in a few minutes. I measured the height of the pole, 93.9 centimeters, and this minimum shadow length of that pole, which was 34.1 centimeters. If I take the ratio of them and do something called the arctangent, I can find the angle of the sun above the horizon at true local noon. Now, I know a lot of your viewers don't know trigonometry. That's okay. Don't worry about it. Suffice to say, there's a way to calculate the angle of the sun above the horizon if you measure the length of the shadow here and the height of the pole.
Well, that's a really interesting way to be able to figure that out, Dale. We're going to have to take a real quick break. For those of you, you can see the email down at the bottom of your screen. Please send us an email with a question if you have one. And we'll be back with part 2 of this discussion right after Term of the Month with Stephen.
Thanks, Don. The term of the month is escape velocity. There are 5 probes built by humans that are coasting their way out of the solar system, never to return. And that's because they are all leaving the solar system faster than their current escape velocity. Let's take the slowest of the 5 as an example. That's Pioneer 11. Right now, Pioneer 11 is moving at 11,000 meters per second relative to the sun. Escape velocity at that distance is the square root of 2 times g times n divided by d, so the square root of all of that stuff, where g is the gravitational constant, 66 trillionths, the units are in meters, kilograms, and seconds. And m is the mass of the sun, 2 billion trillion kilograms, and d is the distance, 7 trillion meters from the sun. You plug the numbers in and you get an escape velocity of 3,899 meters per second at this time for Pioneer 11. So Pioneer 11 is going 11,000 meters per second, so it's going nearly 3 times escape velocity. It's not coming back. In the top view, Pioneer 11 is near the bottom between Voyager 1 and Voyager 2. New Horizons is behind because it left Earth so much more recently. But New Horizons is going faster and will eventually pass Pioneer 11. New Horizons will not catch up to Voyager 2 because it's not going as fast as Voyager 2. And that's because the Voyagers got a big speed kick when they passed Jupiter by going closer to Jupiter and therefore into the higher radiation zone. The 2 Pioneer probes are no longer functioning. The Voyagers and New Horizons are still doing science. And that is term of the month, escape velocity. Back to you, Don.
Thanks, Stephen. We're back with Dr. Dale Partin talking about a poor man's measurement of longitude and latitude. So where do we go next, Dale?
Okay, so from this data, I found out what time the sun passed over my meridian and gave the shortest shadow length. And I found the angle of the sun, 70.04 degrees above the horizon. So then I can calculate the longitude. The time the sun passed over me was 1:29 p.m. Eastern Daylight Time, which if I add 4 hours to that, because I'm in the Eastern Time Zone and Eastern Daylight Savings Time, that gives me 5:29 p.m. Coordinated Universal Time, or Greenwich Time. And if I convert that to a fraction or a decimal, I get 5.483 hours, 15 degrees per hour. Multiply that, I get my longitude, 82.25 degrees west longitude. A poor man's measurement of longitude. The error in that measurement is about 0.65 degrees, which works out to about 34 miles. So it's not super accurate, but between friends, it's in the ballpark.
Hey, I can say it puts us in the ballpark, Dale.
Yes. Then if I take the accurate time when the sun passed over my meridian, which I found out from the internet, I was off by about 2.5 minutes. But reasonably accurate.
I would say.
So that raises an issue. What else can you do with such measurements?
Exactly.
Amazingly to me, I could actually find the size of the Earth, my latitude, the tilt of the Earth's axis, and the length of the year from these kind of measurements.
Oh, that's amazing.
It amazed me. You can see here a plot of the maximum angle of the sun on different days of the year in the year 2005. So in approximately June 21, the sun reached its peak angle above the horizon. But on a certain day, we went and visited relatives in Kentucky, and I took my apparatus along and measured the angle of the sun at true local noon there. You can see that in red. Because of the curvature of the Earth and Kentucky being south of us, the sun was at a higher angle, about 3.84 degrees, higher than it was in Michigan at my location at my house. From that, I can find the size of the Earth the way the ancient Greeks did it, by the way.
Oh, that's true.
If you look, here's the Earth, and you can see where Michigan and Kentucky are. The sunlight comes in from the right, and they cast shadows. So the shadow length at the same instant is going to be a little different in those two locations because of the curvature of the Earth. That curvature is 3.84 degrees different. And from a map, I knew that the distance between those points was 255 miles. So it's 360 degrees all the way around, divided by 3.84 degrees, times the distance between those points gives me a circumference of the Earth of 24,860 miles. Or actually 23,900. The accurate number is 24,860 miles. That's correct within 4% to know the size of the Earth. I'm amazed what the ancient Greeks figured out how to do.
That truly is an amazing feat, yes.
So if you look at all of my data, I fit it with a sine wave. So you can see how the maximum sun angle peaks on a certain day. That's a summer solstice. And 3 months later, we have the autumnal equinox. And then another 3 months later, the winter solstice. So from these measurements, I could find out my latitude, which turned out to be 42.74 degrees, and the tilt of the Earth, this angle here or here, 23.46 degrees. It's off, my measurement is off by 0.02 degrees. I could even get the length of the Earth's year within a small fraction of a day, the length of the year within 0.02% error. I was just amazed at what all I could get out of this. I might say that I went on to copy measurements made or replicate measurements made by the ancient Greeks to measure the distance to the moon, the size of the moon, the distance of the sun, and the size of the sun. Incredible what the ancient Greeks did. I replicated that, but that's a story for another day.
Yeah, that's something that's always amazed me too, because today we have a decimal system of counting and math. They didn't, and so the fact that they were able to come up with reasonably close numbers without having the advantage of a math system with decimals is truly amazing.
I completely agree. They had fractions. They didn't have, I mean, sort of like Roman numerals. They used their letters to represent numbers in their fractions.
Yes, they did, yes.
But the math they had was crude, and yet amazing what they did with it.
Yeah, it is, as you say, amazing when I think of those types of measurements, their ability to put together the Antikythera mechanism. We did a show on that several years ago, and the accuracy was remarkable. I think one of the hindrances of that was the inaccuracies that were built into the mechanism itself, but the fact that they were able to actually come close and get an analog machine to do that is amazing.
Fully agree. So I've replicated a lot of stuff they did. I'm impressed by them and impressed with what a poor man could do to measure latitude and longitude. It's not just about getting a super accurate measurement, but going through the process of measuring these things and coming to have a better understanding of latitude and longitude itself and its utility.
Yeah, it's quite something. And like you say, you did it on a shoestring budget. There weren't any $600 hammers involved in figuring this out. So
nowadays, with a cell phone, you can ask, what's my latitude and longitude, and bingo.
There you go. But that takes all the fun out of it.
Yeah, well, I had to learn how to take square roots by hand when I was in grade school, and hand calculators do that rather nicely now.
Yes, they do. Well, I even remember when having a calculator in math class was cheating.
I remember when hand calculators were a new thing.
Yeah.
They were an expensive jewelry item, as I recall, when they first came out.
Exactly. Those were the days.
Yeah.
Well, Dale, is there anything else you want to toss in, or have we pretty much covered the topic, you think?
I think we've kind of covered it. As I say, I later went on to extend these measurements to doing measurements on the moon and the sun. Quite enjoyable for me. I enjoy measuring astronomical things. When I first got into astronomy, actually doing astronomy back in 1997 or 8, first thing I did was measure the orbits of the 4 Galilean moons of Jupiter.
Wow, that's amazing. Dale, I want to thank you very much for taking time out of your day to be on our program. Please visit our club website. The address is down there at the bottom of your screen. And coming up next with What's Up in the Night Sky is Stephen.
Thanks, Don. What's up in the night sky for August 2025? The days are changing faster as we approach the September equinox. The days are, of course, getting shorter in the northern hemisphere and longer in the southern hemisphere. Wait, isn't it summer? Isn't it supposed to get hotter? No, days are getting shorter, getting longer up here. Anyway, August starts with first quarter moon on August 1st. And then the full moon is on the 9th, the third quarter is on the 16th, and the new moon is on the 23rd. And then the month ends again with a first quarter moon on the 31st. There's no word for 2 first quarters. Then we have Mercury, Venus, Jupiter, and Uranus shown on the 31st of August, 2 hours before sunrise. We're just going to look at Mercury. Mercury goes from Cancer to Leo and sets about half an hour after sunset. It's best at the end of the month, but maximum western elongation is on the 19th, and that should be, as far from the sun as it gets. So that's also, around then should be also good. Mars, shown again on the 1st, about 2 hours after sunset. It's in Virgo, and it sets about 2 hours to 1.5 hours after sunset, so it's better at the beginning of the month. Then we have Jupiter, Venus, Uranus, Neptune, and Saturn, again on the 1st, about 2.5 hours before sunrise. Jupiter is in Gemini and rises from 2 to 4 hours before sunrise, so it's better at the end of the month. Venus goes from Gemini to Cancer and rises 2 hours before sunrise all month, and it is better for reasons that are inexplicable, but it's math. So it's better at the beginning of the month. Uranus is in Taurus and rises from 4.5 to 3.5 hours after sunset, so it's better at the end of the month. Neptune is in Pisces and rises from 2 hours to an hour after sunset, so that's also better at the end of the month. And Saturn is in Pisces also and does much the same thing, 2 hours to 1 hour after sunset. Then finally we have Neptune, Saturn, and Pluto, but we're only going to talk about Pluto because we already talked about the others. And this is arbitrarily on the 15th of August, and it's maybe 10 p.m. local time. Pluto is in Capricornus, and it sets from an hour before sunrise to 3 hours before sunrise, so it is better at the end of the month, actually at the beginning of the month. But Pluto is good at the moment because we just had opposition in July, and so Pluto is up most of the night, so you could see it at near local midnight, and it would be as high in the sky as you're going to see it. So if you've got a scope that's 10 inches, maybe 12 inches or larger, and a decent finder chart, go for Pluto. And that is what's up in the night sky for August 2025. Now, remember, we don't charge money for this show, but we may tax your brain.